And I'm going to start by a huge acknowledgement in this presentation to the second name on my slide, Saverio Spadea. So Saverio was a research fellow for me in this project and has since joined the University of Dundee as a lecturer in structural engineering. So he was sort of the full-time research fellow on the work that I'm going to talk to you about today. So thanks to Saverio. He's not here today, I don't think, but he's, I think, joining us online. So I'm going to talk about this project, Knitting Bespoke Reinforcement for New Concrete Structures. And over the next sort of 45, 50 minutes, I'll tell you the background to why this project came about, some of the research that my group does. We'll talk about the materials, the construction, some beam tests. Then we'll look to the future, so what's going to come next, and finish up with some conclusions and obviously your questions. Now I'm standing here very rigidly because I'm aware that the people online want to be able to hear me, so I need to speak to the microphone. I normally wander around, but I can't do that, I'm afraid. I also have some props with me, so I won't pass this around, but this is an example of the kind of thing that we can make. It's a scaled down model of a beam, as you can see. I won't pass it around because it's a little bit pokey. I don't want to cause any damage to eyes, but please do come and have a look at the end. Obviously, the people online will just have to look at the photos. And as we go through, I hope you'll see some new images of concrete structures, some new types of shapes for concrete, some new thoughts for concrete structures. And the purpose of this presentation is really to get to the point where we understand why this machine was built and why we wound fibre-reinforced polymers into a reinforcement cage for concrete structures. So, the driver for the research that I do is largely in the field of sustainability. And you might have seen a slide something like this before. We have a hugely ambitious, legally binding target of an 80% reduction in CO2 by 2050. Okay, it's a really ambitious target for the UK. And other countries are starting to follow suit. So we have the recent agreement in Paris 2015, or COP21, to sort of limit temperature rises to 2 degrees. So we're all starting to deliver or to try and deliver on this reduction of CO2 emissions. Now, at the same time as that, if we think globally, we've got a growing population. 7 billion people on the planet today, 9, 10, 11 billion by 2050. So huge population growth, potentially in the same period to 2050, and increasingly living in cities. And there's one statistic which I really like to sort of illustrate the scale of the problem, because outside of the UK mainly, China is expected to add 350 million people to its urban population in a relatively short space of time, around 15 years. That's sort of like taking the entire population of America and moving them into brand new cities in a really short space of time. And you can see immediately there's a huge challenge there, a huge challenge in terms of what materials we should use to achieve that, and how we can do that sustainably. We're building the infrastructure, the roads, the buildings, the houses today that we're going to use for the next, hopefully, 120 years. So by 2050, 2/3 of the world living in cities, and as I say, this needs to be developed sustainably. And the reason that's so important for us as structural engineers or architects, clients, contractors, whatever your role is that we have such a huge impact on the emissions that are made. So about half of all emissions are influenced by activities in the built environment. So you have a sort of a key role to play. Over the last 25, 30 years perhaps, there's been a real focus on reducing operational energy in structures, so the lighting, the heating, air conditioning, the energy we need to run our buildings. The reason it says EU and then EU again is it was supposed to be a flag, but it's obviously not translated from my computer to this one, never mind. And other countries are following suit. So the EU Nearly Zero Energy Directive, whether or not we're going to follow that, I don't know, but 2020 to have nearly zero energy buildings. That's a really ambitious target that we should follow, I believe. So the traditional view of whole life energy use being mainly made up of operational energy and a small part being embodied energy is starting to change. And as we have a decarbonisation of the energy supply, better building fabrics, more efficient appliances, all of these things reduce our operational energy use. So the proportion of your whole life energy that is from the embodied energy, i.e. the materials, goes up. And lots of studies in this area. It's a very sort of current topic, but an interesting paper from 2010, so actually 7 years ago now, showed a 70-30 split in an office building in a city centre looking at a 60-year life cycle. So 70% of the whole life energy from the embodied energy in your structure. So that's the stuff that you as an engineer have a real handle on. You can define how much material goes into a building. You have real control over that. And if we do move towards truly net zero operational energy buildings, then obviously it's 100% embodied, 0% operational. That's probably almost impossible to achieve, but we should aim to get somewhere near to it. So what I'm going to show you today is possibly some thoughts which might change what structures look like. So this is a photo I took in Beijing just 6 months ago. And you've got a concrete frame structure going up. It's kind of traditional. We expect to see these sorts of shapes. But hopefully you'll see that through this presentation that changing these geometries might be a very sensible thing to do. Not just from material efficiency perspective, but also from a productivity perspective. And changing the way we actually build structures could be very sensible. And the reason I say this is productivity. And this is a graph from an amalgamation of data from 7 countries, including the UK and the United States. And you see data from 1995 to 2011. Productivity in construction has flatlined. Okay, so we're not really getting better in terms of our productivity. Manufacturing, by comparison, has nearly doubled in the same period. And they do that through what we call lean principles, which means learning from performance, but also through increased automation. So the use of robotics and cobots and so on. In the UK specifically, you might have seen a recent BBC News article which talked about UK productivity. This is a graph from 1999 to present day. Black line is actual productivity. In June 2010, after the recession, after that dip of the recession, the predictions were that we would pick up our productivity at the same pace as before, the red dotted line. That didn't happen, and successive predictions have said the same thing. So those orange dotted lines are the successive predictions that people have made, or the Treasury have made. What's actually happened is we've flatlined. So we do actually have a real challenge in productivity. The blue dotted line is the current best prediction, and you see it's somewhere between the pre and post-crisis averages, which is interesting. And the reason I put this up there is that construction is such a huge part of this overall puzzle. It's 10% of UK GDP, it's 13% of global GDP, and if we can help solve the productivity challenge in construction, we will be contributing to making this graph go back towards the original pre-crisis average. So we're really here to talk about concrete, so I'll try not to diverge too much from that. And this is a photo, you will all have seen this structure before, at the Pantheon in Rome, so 2,000 years old. And I'll say something a little bit controversial. I think if we had a time machine and we took a Roman from 2,000 years ago and brought them to today, the ways that we make concrete haven't changed all that much. The Romans would have made a reed or a timber box and put concrete into it by hand, perhaps with some stone facing. And what we do today is we make steel or timber boxes and we pour our concrete into it. And so, whereas other sectors have been driven by increased automation and these lean principles, construction hasn't really changed all that much. We pour this fluid material into a handmade mold around handmade and hand-fixed reinforcement, and as a result, it's quite an expensive thing to do. The estimates vary, but around 70% of the cost of a reinforced concrete frame is associated with the formwork and the reinforcement. So in this presentation, I'm going to touch really briefly, I think I've got 3 photos of formwork, but really we're here to talk about this stuff, which is the reinforcement. To just give you a flavor of why this is so important, why I'm talking about it, is if we could reduce construction costs by 1%, just 1%, we would be saving society $100 billion per year. And to put that into context, that's the total annual cost of cancer drugs is $100 billion per year. If we could close the productivity gap, we add 2% to global GDP. Okay, so that's a huge reason to do this. And for those of you who follow sort of government reports, you'll have seen Construction 2025, which was released in 2013, and that includes some targets. They're not legally binding, but they are targets to reduce, amongst other things, to reduce initial and whole life costs by 1/3 by 2025. So that's a really ambitious target, which perhaps we won't meet, but maybe we should try and do so. But we want to talk about concrete. This is some concrete being cast. I'm sure we've all experienced concrete at some stage. We've all used it, I'm sure. We have a love affair with the material. Nearly 2 cubic meters of concrete per person per year is cast. That's a lot of concrete, 4,500 kilograms of concrete each. 4.2 trillion kilograms of cement manufactured to make all that concrete. And more than 5%, somewhere around 5 to 7% of global CO2 emissions come just from manufacturing cement. As you will remember, cement manufacture requires lots of heat, which is energy intensive, and therefore we have lots of emissions. Now, I actually don't have a huge problem with using lots of concrete in and of itself. That's kind of okay. We need, as I said, we've got an increasing global population, we've got increasing urbanization, we need to build bridges and roads and tunnels and so on. So that's all fine. The problem arises when we look at our structures and we say, in this building, how much of that material is being utilized, structurally utilized? What's your utilization factor of the material? Do we really need buildings where all the columns are the same size, all the beams are the same size, all the slabs are constant thickness? And the answer is no, we don't. And when you look at the studies of these buildings, then we find, on average, and it varies, of course, but on average, about 50% utilization is common across buildings. So the two studies here cover both concrete structures and steel structures. So it applies to both of the materials. I'm obviously going to focus on concrete today. So that's why I want to suggest that we can start to think about other shapes of structures which help us to improve our utilization. There's no reason to waste material. We shouldn't be doing that by default, which can help us answer some of these challenges. So my group really looks at the lightweighting of concrete structures. Every time I put this slide up, I wonder if lightweighting is really a word. I think it is now that I've said it enough. And really what I do is I say, well, we've got this material, concrete, it's wonderful, it's a fluid, we can pour it out of a bucket, pour it out of a hopper. So if you make the mold the right shape, you can make a concrete structure. So this is a project in Miami, actually. An artist decided to make a banana curved T-beam, okay, as an art installation. So we don't want to do that in our buildings, this wouldn't make sense, but a structure where you put the material only where it's required and you use only the right amount of material does make sense. So if we make the mold the right geometry, we can make optimized concrete structures. They are, it's not impossible to cast concrete into a mold of any shape. Now, in this presentation, we'll talk mostly about strength and stiffness and that kind of thing, but I just want to remind you all that optimization is not just those two things, and that we can include durability, strength and design life, architecture, and very importantly, well-being. How happy are the people inside your building? All of these things go together in the idea of optimization. So we shouldn't forget all of that. So my group looks at this sort of lightweighting challenge from a couple of perspectives: the analysis and optimization, the mold technology, and also the reinforcement technology, which is what we're going to talk about this evening. And that work has been, as I say, primarily the work of Saverio, who was, as I say, the research fellow on this project, but also some PhD students, Yuan Zhang, and a master's student, Kristin, who worked on this with me during the past couple of years. So this was a project funded by the EPSRC, and we set out really to address two main challenges. So the first challenge was all about what happens when you move from these prismatic structures at the top to your optimized geometry at the bottom, where suddenly variations in cross-section, variations in elevation are becoming common. What do you actually do then? Because the internal reinforcement for such a structure can become quite complicated. Everything is quite unique, and you might save material on paper, but it might take you a lot longer to fix all your steel or your FRP, and the savings are lost in the cost and the time, the complexity to do this. And so the first challenge was to say, well, how do we do this reinforcement of complex geometry structures in an effective way? And the second challenge relates to this photo, which I took in Montreal last year. This is a bridge, or an interchange, sorry, from 1967-68. It's a huge spaghetti junction style interchange, lots of bridges all crisscrossing, and they're all being replaced. They're all still in use, but they're building the replacement underneath and interweaving. It's quite interesting. But it's only 1967, and you've got significant cracking, and often quite worrying inclined cracking. You've got corroded reinforcement, you've got spooling. The whole thing is covered in netting to stop the concrete falling on the cars below. And this is a challenge that we have still today to provide durable and resilient infrastructure. The EU, or across Europe, sorry, we spend around about 5 billion euros a year repairing concrete structures. So it's still a huge challenge. So those two things we look to sort of not necessarily solve, but begin to look at or begin to address in this project. And it's called Knitting Bespoke Reinforcement, and there's a website where you can find lots of the information, the publications and so on, if you're interested to follow up. I should make a note here in case one of my colleagues is watching that the process by which this cage was made is really a winding process rather than a knitting process. Although it is possible to knit fabrics out of carbon, in this particular project it was actually winding. So you'll see some images in a second. But what we tried to do is to use commercially available glass or carbon bars as longitudinal reinforcement. And the innovation is in the winding of the transverse reinforcement in the web. So your crisscrossing truss geometry, which you can see as I move this around, and how we design that, how we put it into practice, what the capacity is, and so on. So to illustrate all of this, I will go through a bit of background on materials and design, the construction process, how you might use it, and a series of beam tests that we completed to sort of illustrate the process at a large scale, so still lab scale, but big for laboratory testing. So materials. So why not use steel, or what's the difference between steel and FRP? So there's a corrosion problem still with steel occasionally. When you have low carbon cements and you change the pH, steel has some issues with that as well. It's heavy, which is a problem when you're trying to do things with robots and automation and so on. But it does yield, which is a really great property of the material, and it can be bent on site. So you can bring a whole bunch of straight bars onto site and you can make them up into whatever shapes you like on site, okay? So that's an advantage of steel. FRP, by contrast, is very durable, doesn't rust. It doesn't matter what the pH of the surrounding concrete is, low carbon cements are fine, etc., etc. It has a range of mechanical properties, which is a challenge and an advantage, whereas steel, you expect a yield strength of 500 megapascals. FRP depends on who you buy it from, so who the manufacturer is, which is a challenge in itself. It is very lightweight, and you can't bend it on site. If somebody gave you a straight glass bar, like one of these, and you tried to bend it on site into a rectangular stirrup, you would simply break it. So you have to do things in a factory, which means it's really well suited to making complex geometries, because you have to do it in a factory anyway, so use those factory conditions to make something complicated. Stress strain curve, carbon fiber, high quality, we can get up to 5,000 megapascals tensile strength, and the stiffness can be 240 gigapascals, so similar to steel. Glass is less stiff and less strong, so it's around the 2,000 mark in terms of strength, and then you've got the two lines for steel and concrete down the bottom somewhere. So that's the kind of difference in materials that we're talking about. The weight thing is really, really important, because I'm picking this up. Not that I'm very strong, but that this is really light. Density of wound FRP is about 1,400 kilograms per meter cubed. Steel, of course, 7,800. This is actually really useful if you're starting to move things around, put them into molds, turn them on a machine. Having lightweight materials is actually really helpful. In the work that we've done, as I say, FRP material properties do depend on where you buy them from, which is a challenge. And in our particular project, we use 50,000 filament fiber reinforced. This is the raw material, I should show you. This is what it starts its life as. It's a flexible piece of carbon. 50,000 filaments are in here, and that's wound in a number of layers to create our transverse reinforcement. I won't actually pass this round, but you can certainly come and look at it afterwards. If you do look at it, please hold it by the tabs at the end, just because the fibers can irritate people's skin. And the resin is a Fife resin. The resin is there just to hold everything together. It doesn't add strength in that sense. It's just to hold it, give it a rigid cage. We could make, and we have made these without the resin, but you can imagine it becomes very floppy and difficult to move around if you don't have resin in the structure. So, when FRP started to be used as a replacement for steel, a lot of the initial manufacturing of FRP tended to copy steel. And so we ended up with FRP links which had the same shapes as steel links, and we had longitudinal bars with the same surface deformations as a steel. And it was kind of understandable to do that because you wanted people to pick up this material, and if you made it look the same as steel, then perhaps people would use it. But actually, as I've just said, they have really different mechanical properties. FRP is linear elastic to failure, brittle, steel yields. We should think about them very differently. And particularly, if we're going to start making unusual shapes, then why not make advantage of the fact that your carbon fiber starts its life as a really flexible material. It's just like a cotton or anything that is woven. And we can use that as our advantage in the material. Even when it's covered in resin and it's wet, that is still a flexible piece of material because the resin takes a few hours or a few days to cure. And so we can start to think about this in a completely different way. And so the image on the bottom right is one of the early beams that we did, where in that structure you've got a complex geometry, varying geometry. It's been optimized for its load conditions. But inside of it, you've got glass bars, you've got carbon fiber wound, which is the black lines, and you can see that's a complex geometry. And you've also got yellow spirals through that structure. And the yellow spirals are there to confine your concrete in compression, which is a really important part of the design process, which we'll talk about in a second. And so rather than making it look like steel reinforcement, we just use the materials how they are best suited, which seems to us to make a lot of sense and a good way to offset some of the disadvantages of the material and capitalize on its advantages. So FRP is linear elastic. So if you're going to design a reinforced concrete beam with FRP materials, which I'm sure some of you have done, you want to avoid the rupture of the longitudinal bars. So you have an over-reinforced section, you want concrete to crush, and you provide your transverse reinforcement exactly as you would in any other structure to avoid shear failure. Okay? You also provide or can provide transverse FRP to confine the concrete and increase or improve the deformability of the material before failure. And that's a really important part of the use of FRP. And to illustrate this, I'm going to talk about the difference between hydraulics and elephants. And the elephant emoji on PCs is much less sophisticated than the elephant emoji on Macs, which is why this looks a little bit strange. So we'll start with the picture on the left-hand side. This is a lab test, right? So this is one of the beams that I tested. It's actually a steel reinforced beam, but the principle is the same. We take our structure into the lab, and we apply loads with hydraulics, literally a piston with some oil behind it. And that's the vertical yellow cylinders. As you apply your load, your structure responds, and you're testing your structure in displacement control. You're moving it down, and you're getting a response to the structure. So you see the blue dot moving across. As you reach that yield point, in this case for steel, then your load flattens off, and you can no longer increase the load. It's not possible to do that. You can't pump the oil fast enough. It's a displacement control test. That isn't how the world works. Elephant A has a certain weight, baby elephant, stands on the middle of your beam, and it deforms a bit, and the elephant walks off, and everything's fine. You didn't know how close it was to failure. You didn't know how close you were to that flat line. You have no idea. Elephant B is older and fatter. As soon as the elephant stands on your bridge or your beam, the beam collapses. There's no warning of failure, it just collapses, it doesn't have the right load capacity. So what this really underlines is the importance, one, of knowing what the loads are. So what are real loads in buildings? That's another question. But also understanding the difference between deformability, which we can achieve with FRP, and ductility, which we wouldn't achieve. And there's a really lovely paper by Chris Burgoyne, the reference at the bottom, which goes through all of this in much more detail and talks about seismic and so on. So the basic principle is we design for deformability, we confine the compression zone to improve that response, and by doing so, we can have really sort of easy to understand optimization processes for our structures. So this is the image of the beam I showed before. It's actually a 12-meter long beam. This is a real concrete beam cast by Professor Mark West at the University of Manitoba. And the basic design process for lots of optimization methods is to take a sectional approach. And so you walk along your beam, and at every section you say, what shear capacity do I need, what bending capacity do I need, what torsion capacity, et cetera, et cetera. And you design all the sections and join them up, and then you have your optimized geometry. And we can follow the same kind of process with wound fiber reinforced polymers. So you can see the iterations going on in the image below, but the basic principle is we say, what are the design parameters, what's the loading, what are the materials, we optimize for flexure, for shear, for serviceability, all of those things can be included, as you would normally do, and we have, at the end, an output which would be the beam and the reinforcement geometry, which satisfies all those criteria, which you could say are, you define those, you're the designer, you tell me what your serviceability criteria are, what the loads should be, etc. We can design that. In Flexure, FRP is not much different to a steel design. The only thing you have to remember is it's linear elastic, so there's always iteration. There's no FY to save you. It's just an iterative process, and we want the concrete to fail rather than the FRP. If you imagine a simply supported beam with a uniform load on it, and you just optimize for flexure, the shape that you get is the bending moment diagram. You get a smiley face shape of your beam, okay? So immediately your longitudinal bars are inclined. Now, inclined longitudinal bars help you with shear capacity. So you might have a shear design method which maybe includes concrete contribution. If you're not from Europe, you would have an FRP contribution, you have inclined bar contribution, this T sine alpha. All of this can help you with your shear capacity in these end zones. So it's another part of the iterative process. What's the inclination of the bar? How much capacity does it provide you in shear? That sort of image might not be familiar, but this one certainly is, because this is in the Eurocodes, and you can already do this with steel reinforced concrete. You can use the inclined compression or tension chords of your truss model to give you vertical capacity. And I believe that there is going to be an FRP Eurocode document at some point, although I don't know the exact date. And so we follow a similar procedure. We have a sectional design approach, and in a lot of the work that we've done, we've used the Canadian design code for FRP, which exists and we can use, and that's been very successful. The only other thing that we have as a sort of a challenge is you can wind your carbon fiber around the bars in all sorts of different patterns. You can make a truss-like pattern, you can make a very closely woven pattern, a very far apart woven pattern. How do you decide what the pattern should be? That's not a question you would normally have in design of shear reinforcement. And so this is just going to illustrate that sort of challenge, that question, with a few tests, so 8 beam tests that were done by Yuan Zhang, a PhD student at the University of Bath, where we look at the variation between patterns and reinforcement ratios. So if we look at 2 beams to start with, they have, or I should say, they all have the same span, the same shear span as well, 400 millimeters, point load applied from the right-hand side. They all fail in shear. These 2 beams have the same reinforcement ratio, i.e. the same total amount of wound carbon, but very different failure loads, 50% different. So by changing the pattern, we can get better performance. And hopefully it kind of makes sense that the more distributed, thinner legs gives you a better shear capacity. We can get greater strain into each leg, which means we have greater vertical force, which means we have greater capacity. We also avoid bundle effects, where if you have lots of fibers in a bundle, that's definitely weaker than a small fiber bundle. So as it gets bigger, your stress goes down. The other interesting thing is if we double the reinforcement ratio, and we compare T2-2 and T3-1, so twice the reinforcement ratio, almost the same load capacity. So we have this really interesting way to play with the pattern and understand where should the carbon go. So what we want to do is to minimize the amount of carbon fiber you have to put into your structure. So that's another challenge to do. Not only minimize the concrete and the shape, but also minimize the carbon fiber that goes into it. So the analytical methods that we develop, which, as I say, if you look on the website, you'll see all the publications which are coming out, based around CSA and ACI methods, so Canadians and Americans, and also what's called the modified compression field theory, which is the basis of the Canadian concrete code, actually, not just FRP, but all concrete codes. Very good design method for shear. And the work of the PhD students at Bath has improved this method to include the inclined bars and the vertical contributions and so on. And so we're getting better predictions of capacity, which is what we want. We want people to be able to say, how strong is my beam, without having to test every single shape under the sun. One key limitation of all FRP materials happens at the corners. So for those, I don't know how good the video is, I have no idea, but hopefully you can see I'm waving this thing around. The bars in this model are quite small, and so the FRP that's wound around them has a very tight corner radius. And so what we understand with all FRP materials is that failure is usually governed, or often governed, by the corner strength. And the reason for that is we have stress or strain concentrations in the corners. And you get a reduction in capacity compared to the straight tensile strength at the corner. And it can be quite significant, in fact, very significant. So why that happens in a circular piece of FRP, made into a rectangular stirrup, is at the corner we've got normal stresses, we've got bond stresses. We also have the potential for kinking of the fibers on the inside of the bend and stretching of them slightly more on the outside of the bend. All of these things, once the stirrup is placed into tension, cause premature failure at the corners. And that's included in design code, so you don't actually have to worry about that if you're doing a traditional circular cross-section stirrup. The ACI method has a ratio between the radius and the diameter. The Canadians just simply say you lose 60% of the tensile strength. So that's how big the loss is. You lose 60% of the tensile strength in the corners. So the question that we asked was, well, first of all, we presumed that the same effect happens in this system, but what was the magnitude of the effect? And was there anything better about having a wound system as compared to a circular system? And the answer is, yes, it is better. And the reason for that is our cross-section of the transverse reinforcement is rectangular. So we have a smaller difference between the inner and outer fibers at the corner, and so the strain difference is much smaller, so tighter radii become possible. You can imagine in the diagram here, WF can be quite large, and TF is quite small, in the order of millimeters in this case, in this model here. And so we can get, for the same area of FRP, we can get greater utilization out of it by minimizing the strain concentrations at the corner. And that's really important if we want to actually use this in a real structure, because the corner strength will govern your shear capacity. Okay, so the way that we developed the design guidance, or the test methods, was to start initially with an ACI method for testing corner strength of FRP. Now, the ACI method uses two massive blocks of concrete and a large link, which you embed in the concrete, and then you push the two blocks of concrete apart. Those blocks are large, 500 by 300, and the link in the middle is quite small. You can just about see in the photo now, at the top and the bottom, beneath the yellow cylinder, which is the jack, you can see the legs of the link. So they're really dainty, and you've got two massive blocks of concrete either side. It's actually quite easy to damage that system. And so Kristin Ivanova and Saverio developed an alternative method which didn't require making huge links like these. We used a smaller, scaled-down version to help us understand the behavior of these structures in the corners. And so the revised method is much smaller, 300 millimeters in total height, with a link going between two blocks of concrete. I can't point at the screen because the people online can't really see what I'm doing, but you see the link going between the top and the bottom, and we pull those two things apart. And the video on the right-hand side shows you how quick that test is. We can change the samples over, we can test lots of different geometries very quickly. So it has lots of advantages in the process of testing. And this is, again, really important because a lot of the design codes are based around empirical data. They need lots of test data to validate and calibrate them. And so lots of specimens were tested with a range of layers of wound fibre-reinforced polymers, and what was found is the bend strength does improve at those corners with our wound FRP as compared to a circular section, and that is, as I say, very advantageous for us because we want to have tight radii in our beams, in our real beams, and the wound FRP process gives us that rectangular cross-section, which is incredibly beneficial. So that's all detailed in a publication just from last year in Composite Structures. So all of that is fine. We've got a shear design method, we've got a flexural design method, we can talk about patterning, we can talk about the corner strength, the bend strength of this material. But the other side of this is also really important, the actual construction process. So it's actually really simple. This image sort of sums it up. It's actually an old version of the machine. But on the right-hand side, you've got a spool of carbon fiber. Carbon fiber literally comes on a roll like cotton, goes through a resin bath, this thing here, which is a heated resin bath, series of rollers, goes up and down through the rollers. It's coated in resin, which is kept at the right temperature, comes out the end, there's a head which can rotate, and it's placed on a rotating mandrel in exactly the right place as defined by your lovely computer code. And again, this is a sort of version 1 of the machine, but it's the same thing. We have a rotating mandrel, we have a head which moves up and down, and so long as you can control that, which we can with something called G-code, that's how you control machinery, you can put that reinforcement exactly where you need it. And what's really nice about the system is you get a really consistent resin distribution through your fibers. It's going through a series of squeegees, basically. So the resin is squeezed into the fibers, nicely distributed, and placed around your rotating cage, essentially. So we use the fact that it's hollow down the center to make it rotate around the longitudinal bars to create our reinforcement cage. So not only did we do small-scale testing to develop this, but large testing, so laboratory large, so 4-meter long beams are quite large, to verify the sort of the theory and the the behavior of these structures at scale, and primarily using, again, the S806 method. So Severio did these 14 tests divided into two groups, one of which was a large T-beam, so a wide flange T-beam, and the other was a smaller flange joist, concrete strength C30-37. We had glass and carbon bars longitudinally. The two types are shown here. So the T-beam 900 mil wide, and then the maximum depth 190, and the joist, as I say, slightly smaller. So the optimization process was done for the strength, for the serviceability, as we just discussed. The testing, yes, it was using hydraulic jacks, after what I've just said about hydraulic jacks, but that's what we do. So uniform distributed load in the center between the two supports, and a point load at either end, modeling, a facade at the end of a beam, that kind of structure. The purple pattern is where the strain gauges were on the wound fiber reinforced polymers, and then the greeny blue lines are where we have strain gauge cross sections with concrete and FRP. And sort of the headline of this series of tests is that they worked really well. We got the behavior that we liked or we wanted. And this is just a few images, ranges of failures. And some of them look really dramatic, but don't worry, because we intended for shear failures to happen in some of these tests. This is what shear failures look like. And I don't want to go through all 14 beams. I'm just going to pick out two to discuss in a little bit of detail and show you a video. But these load displacement diagrams will look quite different to what you might be used to if you've seen steel reinforced concrete beams being tested. There isn't that horizontal plateau, okay? But we don't have to worry about that because of what I said before about deformability and the fact that concrete crushing can be a failure mode. So don't worry about the numbers. This is all the test data. The important bits are the predictions versus the actual behavior, and the box at the bottom in orange is the average experimental to predicted UDL ratio, which is very good. So only two of these actually fell below 1.00, and they were both 0.99, so we're kind of happy with that. And it's important to realize that in this table we're predicting both flexural and shear type failures. And shear failures are by their nature much more variable anyway, so this sort of ratio is very good to achieve. So we can show that this method works. And so a failure in shear I want to illustrate with one of the joists, joist number 2, just to illustrate what happens. So concrete strain, these are the maximum values. It's about half of its ultimate. The wound FRP got up to over 1%, which is high. So we're getting good strain capacity out of the wound FRP in the web sections. So we wanted this beam to fail in shear. Okay, that's important to remember. As it's loaded, you'll see it starts to deform. And if you watch on the right-hand side, it does fail on the right-hand side. And the images at the bottom are a digital image correlation which uses that black speckle pattern to post-process the strains in the concrete or on the concrete surface. And you can see on the bottom right-hand side that big red line is where the big shear crack occurred. So we know that the system is working. It's actually a very useful way of monitoring your structures. So that's a classic shear failure. It's what we want to avoid in real structures, of course. Of course we do. But in the research, we must understand where that failure happens so that we can design against it. That's why having things fail in shear is really important. By contrast, one of the T-beams failing in Flexure, T5. So we've got a nice high concrete strain and good strains in the longitudinal and wound FRP, so approaching 1% in the wound, but close to failure in the concrete. I should note that strain gauges on concrete are notoriously bad things to be using, but these are discrete measurements at one point on the surface. There might be somewhere else which was higher. You can never know that. It's just the limitations of the monitoring that we have. This is the beam, underloading, and it's well beyond any serviceability criteria very quickly in this video, which is obviously speeded up. This is a hugely deformable beam. That's only 3 meter span, and we're getting up to 100 plus millimeters deflection in the center. This is with supposedly very brittle materials. We've got concrete, we've got FRP. Brittle materials, but nice deformable behavior. So we can achieve this, it is possible. And with all these tests that Severio did, we've established that it's feasible, there's a proof of concept for the optimization, the analysis, the construction methods. And I'll touch on this again in a second, but it's suitable for what we call mass customization. The idea not of mass production, but of mass customization. And it integrates well with flexible formwork. So I can never give a presentation without talking about flexible formwork. So you might be thinking about, well, okay, it's fine to make this. You know, this is the reinforcement cage. What shape is the mold that goes around this to hold the concrete? And the answer is that we used fabric to make the mold. And fabric formwork is literally taking pieces of fabric, high-strength geotextiles, woven polypropylene, in this case in my hand, a geotextile on the screen. And if you hold this in the right way, you can make a mold which is the right shape for your concrete structure to create the kinds of geometries that you see on the screen. So this beam that you're seeing now is a ductile beam, an ultra-high performance concrete beam, cast in a fabric mold to make those ripples, varies in cross-section. This beam is 12 meters long. The formwork for it is one piece of fabric, 12 meters long, a meter or so wide, held in the right way so that when you fill it with reinforcement and concrete, you get this lovely optimized shape. And what's really interesting about fabric formwork is it's just a different way of thinking. No longer do you have heavy pieces of steel, heavy pieces of timber, panels to move around. You've just got pieces of fabric. And so if you're doing fabric formwork, you might be patterning, cutting and stitching, using a sewing machine, using an iron. That was you have to iron your formwork, otherwise you'll get creases in the surface that you cast. Or you might leave the creases in for an aesthetic effect. This is a really interesting way of casting concrete, which ties in with the idea of making bespoke reinforcement. So we have all sorts of possible geometries, be they facade panels, curtain walling, architectural, curvy shapes, all of this cast in fabric molds. My work looks mainly at taking us from those prismatic structures through reducing material use, changing the shapes, and providing not just an internal reinforcement system, this thing here, but actually a way to cast the concrete as well, which is the fabric which goes around it. There are other ways of casting, but fabric formwork is one which we could examine further. So, where's it all going? We've established that it works, the proof of concept is there, but there is, as always, I'm sure every academic says this, further research required, obviously. Analytical tools, concrete, notoriously hard to model. It is a difficult material. If you've ever tried to use Fe with concrete, it has problems. This thing, peridynamics, is an alternative formulation to model concrete behavior. Encourage you to look at that website if you're interested in that. It's another project that I run. Optimization routines, we got an optimization routine to make this shape, curving in elevation, cross-section changes along its geometry. How close are we to the perfect beam? We don't know. Better optimization is always a good thing. The use of pre-stressing. Pre-stressing is a great way to optimize the use of FRP because you can pre-strain the material and that really helps you with serviceability. Automating the mold construction and demonstrating full-scale construction with prototype buildings. So I really put this up there because if anybody has a free piece of land and wants to let us build a building, you can let me know and we'll happily do that. So let's have some more pictures. Why is there a picture of the Great Wall of China? You might be thinking, well, hang on, carbon, the precursor for carbon is polyacrylonitrile, PAN. It's quite energy intensive to make this stuff. Yes, it's flexible, yes, it can be wound, but it's energy intensive. Do we really want to use this? And the answer lies in the trees. So there's been a lot of research, which actually began in the 1960s, saying that we can make carbon fiber from lignin, which is the second most abundant source of carbon on the planet. And today, I counted it up just recently, so I know the answer. There is 100 million euros worth of research going on, funded research going on in the European Union to turn lignin into commercially available carbon fiber. So it's a bio source of carbon. So that's coming. And that is 50% less embodied energy straight away through using the bio source of carbon. The formwork, I talked about fabric. This is my pet project, fabric formwork. I do appreciate that it's still a craft industry, fabric formwork, but the automation of a concrete mold, I don't think is a craft industry. And we're increasingly, through our research at Cambridge, looking at how we can control molds with things like 3D scanners, digital systems, to have continuously changing mold geometry. So no longer do we have big rigid panels of steel that we move around, but we have a casting bed which changes for every single piece that you need to make. And that's where mass customization comes in. And the reason that this is so important is it happens in other industries. We already do this. The next time you go and buy a BMW 7 Series, you might be aware that there are 1 billion, and that's not an exaggeration, I'm sure that I read this on the BMW website, there's 1 billion possible variations on a 7 Series. Yet that is made in a mass production process. You go and design your car, and the the factory in Stuttgart churns it out in the same speed as it does every other one. Mass customization exists in other industries. We should learn from that, because I don't think we should try and have one perfect beam for every building and therefore all offices are the same. I don't think that's a sensible way to go. The other thing we must do is start to learn from how our structures work. I put 3 images up: a plane, a car, and Toronto. I'm not picking on Toronto, I just happen to have a photo. The plane, if you're Rolls-Royce or Pratt & Whitney, you know exactly what's happening in all of your engines right now. There's a control center which will tell you all the data right now of all your planes in the air. You'll know if it needs to be repaired. You know where it can be repaired, who should repair it. All of that is known. Cars do the same thing. Tesla's doing wonderful things with sensors. In buildings, there's very few sensors on the structure. So we don't really know how they work. We don't really know what the loads are. So we have this sort of need to start to learn from performance, not just from the buildings, but from the people inside the buildings. And I'm very keen, as I said at the beginning, with well-being, that we start to monitor the people in as least obtrusive way as possible and understand how things like structural vibrations affect people, and productivity is linked to that. A quick example is there was a study in Australia. The higher up you go a tall building, the more days off sick people take because the vibrations are higher. And there's something called Soppite syndrome which explains this. But we need to understand that, and the only way to understand it is through measurement. So what this work is really driving towards in sort of the bigger picture is going from the current state of heavyweight, uncertain design through to measuring the performance, understanding what's going on, human and structural behavior, understanding how we turn that information into something useful, and feeding back to our designers, to our occupants, to increase certainty, which means we can start to save material. So 30, 40% savings are achievable, I think, now. So we will have certainty in the design process. We might use different methods of design, but we have certainty. And in the even longer term, introducing adaptive structures. This is something which is starting to happen. There's brilliant work at UCL by somebody called Gennaro Senatore, where we have structures which are infinite stiffness. And you might have seen this model at the Building Center recently, where you design for strength and then you control serviceability. And you can only do that through sensing, understanding performance. All of this stuff is very much linked together. So, the knitting project, we've shown that it's feasible to do it. I've got the proof here. It's definitely possible. The design, the analysis, optimization has been shown through the beam testing. It's driving the ideas of material efficiency. It's driving the ideas of automation and robotics, which I think are really important for the construction sector. But from the sort of two ends of the presentation, hopefully you see that that is just one part of a bigger picture, very much a bigger picture, that we have this productivity puzzle, and we need to start to do really different things to change it. Doing the same thing again and again isn't going to save the productivity problem. And we've shown that already. For the past 30 years, we've flatlined. We must do something different. And we do that through measuring real behavior, understanding performance, and then introducing things like automation of design, automation of optimization, and learning from other sectors which do this really well, automation, automotive and aerospace, for example. And investing much more in the cultural change through research, which I hope that we can get industry involved in as well. And I just want to finish with that, the sort of the headline that I really like, that if we could save 1% in construction costs, we'd be saving $100 billion per year. So thank you for listening.